It's about surface interaction between the sample and the staging phase. So the whole thing here is a staging phase, and all these small, they are solid on the sample. Solid refer to the sample, all these small. It's about surface interaction. It's about surface interaction. And this kind of C phase, common C phase example, we have all this. For example, we have the silica gel, we have alumina, we have charcoal or cellulose. These are the examples of the C phase. So PC is about surface interaction. And then this surface interaction, of course, is based on the what? The force between the sample and the safe phase. There's a forces, and these forces most probably is a positive negative interaction. It's more on positive and negative interaction. Means charge interaction. It's more on charge interaction, charge and charge interaction. This is absorption chromatography, and this usually for the all types of separation. And now we move on to see the partition chromatography. And this partition chromatography is more on the what we call the is a sample penetrations of the sample. You can see the sample go in and then come out from the liquid film. So this is a staging phase, and the layer here is a liquid film. It's a layer of liquid film coated on the stationary phase. So permanently coated on the staging phase. So the sample will go in and come out, and this kind of process we call partitioning. It's an equilibrium process, or we call equilibrium partitioning between the sample and the stationary phase. So this process is called partitioning in and out into the liquid film. And this is a chromatography that applied in our GC and the SPLC. So GC SPLC is based on this principle of separation. And now we move on to see others chromatography. IEC here, ion exchange chromatography, IEC is basically these are the, how to say, generally we have a, let me draw some here. It is a stationary phase, and on the surface here, they are coated with certain charge, means a certain compound or function group with charge. It coated with positive here, and this we call as an ion exchange chromatography. An ion exchange chromatography. An ion exchange chromatography. And there's another charge which is temporary interact with the positive charge. This one is temporary, and this will be exchangeable. And since the exchangeable ion is a negative ion, that's why we call anion exchange chromatography. If the ion coated here is a negative, and the exchangeable is a positive ion, then this one become cation exchange chromatography. Because the positive ion is exchangeable, that's why we call cation exchange chromatography. And the general staging phase used in the ion chain chromatography is usually a resin. SP usually is the resin. It's a resin. That's why you can see cation exchange chromatography. The resin here actually is a stationary phase, and bonded is the native ion. The exchangeable will be a positive ion. That's why this is an exchangeable ion. This will become cation exchange resin. And ion here, exchangeable, will be a negative ion. Negative ion. This one is a bonded. Means permanently bonded. This is also bonded. So bonded negative, exchangeable positive. So cation exchange chromatography, exchangeable negative, and anion exchange chromatography. So these are the what IEC here. IEC. And this IEC is the one that you're doing your practical, the last practical, which is IC, ion exchange chromatography, and which is IEC. Then you further reduce, then become IC. So IEC become IC. So this IEC here. Now we move on to see other types of chromatography. Copy there, so we move on to the next one. Size exclusion chromatography here. And you can see there are many pores here, and the porous gel. A small opening here, did the right? I think they're right. So you can see the small molecule can penetrate into the holes of the stain phase. The whole thing is a stain phase. The big one cannot go in, so you'll be come out faster. And now we have a CE or electrophoresis. It's based on the effect of the electrical charge here. So positive go to the cathode, negative go to the anode. So this is usually suitable for. So the separation basically based on the charge and the size, or charge over size ratio. So basically affected by the charge and the size. So they say it's based on the charge over size ratio. So usually suitable for protein sample or the nuclei or particle samples. So this is CE. And now we move on to the next slide here. Here is a summary of different types of chromatography. So generally we have a GC. Here will be LC. LC are liquid chromatography. GC will GLC, gas liquid, gas solid, GSC. Then you can see we have liquid chromatography, liquid solid chromatography, ion exchange chromatography, size exclusion chromatography, or SEC. And you can see this liquid is further developed, means there's an improvement into the bonded phase chromatography. GC here, if you want to write, also can be further developed to the bonded phase chromatography. So they are general types of LCF. And in this chapter, in this paper, we focus more on the GLC. In the GC chapter, and we focus more on the LLC. In the SPLC chapter, why we focus more on this? Because these two two, they are popular or they are more usage. So we focus on the important one. So now we move on to the next slide. Yeah, over this partition chromatography here, GLC and LLC, they are partition chromatography. Solid, gas, liquid, solid, they are under absorption chromatography. And now you can see for normal column chromatography, is a column chromatography, and this is an initial state. Sample, of course, all these are liquid sample. When you first introduce to the column here, they're all together. When they move down the column because of the interaction, and this interaction will be different for different compound. So because of the different interaction for different compound with the packing material, that's why they start to separate. The longer the distance they travel, the more separation you can observe. So now you can see the two compound here. Actually, the two compound now at the end they are well separated, one faster than the other. And there's an important concept here. Those come out faster, it means what? There's a less interaction with the stationary phase. Those come out slower, of course, they have more interaction with the stationary phase. So faster, lesser interaction, slower because of more interaction. That's why you can see the peaks here, and of course here refer to all this separation here, and this refer to here. You can see the two band not really separated. That's why you can see certain degree of overlapping here. And now you can see they are separated. Of course, this one also refer to the same chromatograph. The two, they are separated. So separated, that's why you have I hope the color they use is not distant from the column. Then correct. I thought it's the time. In time, they're not correct. So this one come up. Yeah, a bit so the first band here, I hope it's referred to this band. And this band should refer to this. Descend down the column, so this far away, so this will be the top one, this will be the bottom one. Anyway, this just general concept here. So now we move on to see the next slide. Yeah, it's the same. These two, they are the same one. And now you can see the actual separation using a column, and the chromatogram is the one that the diagram that you get from the separation. Detector signal, this will be the detector signal. Usually detector signal is referred to the peak area. If you should have finished your practical, now it's week 9 or going to finish. This is a peak area detector signal. Here will be the time, or we call retention time. Not concentration. You put concentration, then wrong. It's a time. So it's a retention time, how fast they come out from the column. TM is a mobile phase, retention time. TR1 will be, I think I will write here, TR1. This one TR2, sample 2, TR3, TR4, then 5, then 6, then TR7, and TR8. So you see there are 8 compound here. So these mixtures of sample, the sample contain 8 compounds. So last one will be sample 8. First one, sample 1. And of course you can see here 1, 2, 3, 4, 5. There's some obvious or differences between the signal. Those come out faster, usually the peak is sharper. This the early signals, they have sharper peak. Those at the back, those later peak, they are usually quite broad. You notice the peak quite broad for those come out at the back one. In front one, sharper. So this we'll discuss later on in band broadening, peak broadening section. I will discuss all this again. You just notice the early peak, sharper, and the baseline width thinner. Those at the back, you can see the baseline peak larger. Just notice all this, then enough. And now we move on to the next slide. I think you copied it here, so we move on. And of course, retention time, adjusted retention time. But usually we just use retention time. Adjusted means after this refer to after the use of T minus the TM, you get adjusted. This one just T. This one is TM. It's TR, not TA. So these are the different TM, TR prime adjusted means minus TM. But usually, you can see I never use this one because this one, or we hardly use this one. We don't use this TR. Why? Because most of the time, this one not appear in the analysis. Of course, you didn't do the practical, but in your practical data, you don't see TMP. Either GC or SPLC, you don't see the TMP. That's why I say TR here. Actually, not very practical, so we don't bother this one. Not say don't bother, just understand enough. It's not practical. So now we move on to see others. And of course, the peak here, preferable to have a Gaussian peak. Gaussian peak means you have a symmetrical, you have a symmetry peak. Means the peak is symmetry. Left and right, they are equally equal distance. It's called Gaussian peak. Their symmetry peaks, of course, is given by certain formula here. Here, of course, they look at the middle of the peak, the peak at the middle part, middle height, which is equal to this. If based on the baseline here, at the bottom will be 4 times something like sigma. Middle will be 3.235 times the sigma. Sigma is something like standard deviation, and just multiply the value, you will get the Gaussian peak value using the formula. It means you can get the value, whether good or bad. you see, we can see with your eyes easily whether they are good or bad, symmetry, not symmetry. And all this flow rate already discussed in the tutorial. You can check back your tutorial. What is flow rate equal to what? And now all this I didn't already teach you. Now we move into some new terms or formula of the chromatography. And now we start with this terms here, equilibrium constant. It's a capital K equal to CSCM is a concentration of the sample in the staging phase. And this one is the concentration of the sample in the mobile phase. All this already teach you. And of course, this will happen at equilibrium. All this happen at equilibrium. Happen at equilibrium. And now, should we see? Copy, then you move on and see whether should I tell you the additional thing. And now we can look at the K here. Let's see whether I should talk here or not. So we come back to the K here. And since we know the K is about the equilibrium constant here, it's the equilibrium constant. And this happens during, of course, at equilibrium condition when K equal to 1. And this K equal to CSCM. And when it's equal to 1. It means that the concentrations of the sample in the same phase and mobile phase, they are equally distributed. If K is larger than 1, or I think I write more than 1, then what will happen? And if K is smaller than 1, then what will happen? Equal to 1, equally distributed, you get a Gaussian peak. Remember this is how we talk about Gaussian peak. Gaussian peak, you get a symmetry peak. You get a Gaussian peak, what we call symmetry peak. So if K equal to 1, you get this nice peak. If K is larger than 1, what will happen? Larger than 1, when we have a column, we have steady phase, we have mobile phase. More sample in the staging phase, you have more sample here. Here you have lesser sample, more sample in the same phase. Means time spent by the solid in the mobile phase is short, and more time spent in the same phase. That's why larger than 1. And you can see here what will happen to the peak here. If this is the original signal or symmetrical signal originally, means nothing happened, we get a symmetry peak. If K larger than 1, more sample in the same phase, If more sample in the same phase, two sample in the same phase will come out slower. Come out slower in the same phase one because more come out slower. Slower you get the peak broader here. Because of slower now your peak become broader. If you cause a band broadening, and this band broadening is what we call tuning. It's a tuning peak at the back broader. At the back is broader tuning peak. And now if the K is smaller than 1, you can see here, same phase, lesser sample in the same phase. You have less sample in the same phase. M is larger, so you have more sample in the mobile phase. More sample in the mobile phase. Then what will happen to the signal? If originally the signal is a symmetry signal, what will happen because of more sample in the mobile phase? Remember, if the sample is in the mobile phase, it will come out faster. Two sample in the mobile phase will come out faster. If faster means what? You get broader peak in front. Broader peak in front, and it's called what? In front more peak. It's called fronting. It's called fronting peak. So you see in the SPLC or GC, you get a peak something like that. Just now here tuning, you see something then like that. It's called tuning. Now you can see the difference like that and like that. And this you observe this when you do your SPLC in your FYP. If you do FYP using SPLC, you see all this kind of problem. Then how to adjust? Then you need to do something to adjust the peaks to make it look symmetry. So this is the effect of the K, larger, smaller, and equal. So of course, equal is better. And now we move on. I hope you have copy here. Then we move on to the next slide. I think all this already explained to you in here. And now there's other terms given here. Remember in the column we have a sample. You can look at the column again. Let's draw a shorter one. So we have same phase, we have mobile phase, sample in, then out. And different sample, of course, there are different mobile speed or different migration V. And this V here is for the solid or the sample. And L here refer to the length of the column. TR is a retention time. Different sample, you have different retention time. L is the same. So different sample, different retention time, so they have different velocity or different speed. And for the mobile phase, this refers to the mobile phase, the solvent or the gas. So this mobile phase, of course, LTM is a mobile phase retention time. Mobile phase, of course, usually faster than the sample speed. Mobile phase always in front. That's why you have no need to draw the one. We have the TM. TM always in front. Then you have the TR1, TR2, and so on. So these are the difference between the sample speed and the mobile phase speed. And now we move on to see the other slide. If you want to relate the sample speed and the mobile phase speed, you can use this relationship. Actually, the V and the U can be related in these fractions of time of the sample spent in the mobile phase. And these fractions of time for the sample solid spent in the mobile phase actually is the number of moles of the sample in the mobile phase over the total moles of the sample in the column, which is mobile phase, plus the stationary phase. There are the mobile phase. Remember in the separation, you have a column. You have sample in the mobile phase, you have sample in the stationary phase. So the V and the U is the amount of the sample in the mobile phase over the amount of sample in the mobile phase plus the column, same phase. Here is a total. Means the mobile phase over the everything one will be the relation between the V and the U. And the amount of sample in the mobile phase, of course, cm vm. This refers to the amount of solid in the mobile phase. And here refer the amount of solid in the mobile phase and the same phase. And now remember cm/vm is about number of moles. cm/vm or cv actually is the number of moles. Because C is concentration. Concentrations example we have how many mole per liter. V is a volume. Volume example it can be a liter. So liter cancel is number of moles. Actually that's why I say CV is number of moles. Number of moles actually refer to amount of the solid. Number of moles how many moles mean amount of the solid. And then here you just divide the top part, or just divide with the cm/vm. Top part divide with cm/vm, bottom part divide with cm/vm. That's why you get 1 CS/vs cm/vm. Mean all the parameter here you just divide by cm/vm. You get this equation. And from this equation, what can we see? You can see the V equal to U, and then multiply 1 CS VS cm/vm is what? Is something like CS VS cm/vm. It's the same. And remember we have the capital K CSCM. And do you remember we have the small k CS VS cm/vm. So this small k is capital K. And now you can see here CS VS cm/vm actually is small k. So V now equal to U multiply 1 over 1 plus the small k. So this is a formula. So we derive until here. Then we move on to see the next one. So we move on to the next slide. Copy there, so we move on to the next slide. And you can see here, of course here, they use the capital K. I just ignore the capital K. I straight move into the small k. And just now already derived until here. Until here just now. The small k, they put a prime here. So all this already explained. We directly go into the step here. And now we know that just how we derive until here, the formula. The rest you want, you can go through, you don't need, you don't want, then just follow what I told you just now. So it's not until here. Remember the V is L over TR. L over TR, V. The mobile phase speed is L over TR. L is a quadrant length. How long is the quadrant? Is L. TR is the retention time. Mobile phase is L over TM. And of course, the rest remain. The 1 over 1 plus K here remain. And this parameter, if you rearrange, you get K equal to TR, TM over TM. So this will give us the retention factor K. Give the retention factor K. Capacitor, I did not need you use this retention factor K. And because of the relationship of the flow rate, which is F equal to the V over T. And now we can also write the K equal to VR, VM over VM. Of course, all this you have seen in the tutorial, some of you. So this formula, K is quite useful, TRTM or TM. So this is the way we get the formula here. So you can copy this then before we move on. Copy it here. What else? I think we stop here better. But before we stop, just a remind for you.